Okay, so my talk today is about positive unlabeled data. Let me look at the first slide, and the first slide it's too tall even for me. Okay, so there are some important information here contained. Okay, the first one is that it's joint work with my PhD student Jan Mielniczuk, and let's look at the title. There are some important things in the title, I believe. There's variational learning, which was covered in analysis lectures before, but also we have the second thing, which is biased positive unlabeled data, and I will try to somehow to comment on this because the emphasis is on the bias. What's important is biased here. And okay, so let's look to the short outlines. I will cut very short introduction concerning autoencoders and deep encoding because it was covered, but I will focus on variational autoencoders aimed at solving positive unlabeled data problem. And also, of course, I will give introduction to biased positive unlabeled data. And, well, last 5 or 7 minutes I will devote to our contribution, which is is modifying of VAE-PU by adding one class classification method to that. Okay, so let's start with positive unlabeled data. So let's give a simple example. Probably most of you know this, but let's imagine survey data when somebody is asked whether he's texting while driving, which is considered a sort of dangerous behavior. At least myself shouldn't do that because it will be very, very dangerous. But some people who do that, well, are not ashamed of answering yes, I do text when I drive. But some people, of course, because it's considered not very social behavior, they simply answer no, even if they text when they drive. Okay, so we have a certain problem which we call partial observability, is that simply we cannot distinguish between people who truly do not text when drive and those people who do text but simply do not want to give a truthful answer. Okay, that's the point here. And moreover, which somehow relates to the adjective bias, is that problem whether somebody answers truthfully or not depends on the features. Okay, some people, for example, more highly educated will be more prone to give truthful answer, and some people perhaps, okay, coming from a certain social strata will give negative answer even when they do text when drive. Okay, so perhaps another example which is perhaps more appealing to you is simply when somebody clicks on web page and okay, so this web page can be considered interesting for him, but if somebody does not click on a certain page, it does not mean it is not interesting, but perhaps simply he hasn't time to browse this page. Okay, so that's the point. And please, if you do not have some problems with that, please interrupt me because I would like at least basic to be somehow transferable to you, conveyed to you. Okay, so what we have here is we have, unlike in classical classification case when we have x and y is class indicator, which will be here positive and negative, so y will be 1 and -1. We observe X and O will be stands for observed, and O equal to 0 will be labeled. The observation is labeled, and 0 it means it's unlabeled. Okay, so what comes from this example I have given you is that I would like to consider all labeled observations as positive, and unlabeled observation will be either positive or negative. Okay, and my task is quite standard. I would like to build a good classifier, but of course for Y, okay? So for not observable Y, okay? And of course the other task, which is not usually the analogous one, is to construct good estimator of a posterior probability. That's how it works, okay? So let's look once again as outcome. So this is classical classification task, and here you have positive unlabeled data, so we have this positive class, but you see some red dots are simply replaced by black squares, and this means that those observations are not labeled. And once again, the manner in which those red dots are replaced by black squares depends on the features, and that's very, very important, okay? So let me comment how usually people try to model this. So usually modeling uses so-called propensity score, this probability of being labeled given the positive class, of course, because only those observations are labeled, but also given the vector of features x. Okay, so here we explicitly state that propensity score depends on x. Okay, so what is important here is that, okay, the most common approach here, okay, because people are usually trying to use the principle of the smallest effort, is simply to assume that propensity score is constant, so it does not depend on x. Okay, so it is called selected completely at random assumption, but it does not work in many situations. Usually you would like to have propensity score depending on x. And there are some possibilities here. The first possibility is simply to assume that it does depend on x and only on x, and try to either to model it or simply to use, for example, variational autoencoders to somehow to cope with this situation. Okay, so here we have some, I believe, quite exhaustive list of what is done in the biased positive unlabeled case. One important remark is that I will be speaking about so-called single sequence space, meaning that I have IID sequence containing X's and O's. So that's important here. So here you have, okay, some I believe this exhaustive list of approaches to deal with biased PU situation, and in fact I will concentrate on VAE-PU, VAE-PU, which is in fact the approach we have modified. Okay, so just a very short intro to variational autoencoders. I believe, okay, it was very nicely done, so I will just cut it down to minimum. So we have just simple autoencoders when suffer from the problem that if I encode simply something into low-dimensional data and I do not put any constraints on this, so I will have the problem of overtraining. Okay, so that's why, in fact, the idea of variational autoencoders came into play, because simply the simple autoencoders simply overtrained terribly. Okay, so as you know already, so we had this approach based on approximation of this P of xz, this latent variable here, by some simpler structure, and the simpler structure gives you, in fact, a certain regularization term in evidence lower bound elbow, and that's and minimizing of evidence lower bound is what is done. What is done here commonly. Okay, so let's look at what is happening in variational deep embedding. So here what happens is that Z is usually modeled by multidimensional normal distribution. For variational deep embedding, the situation is a bit different because Z is modeled by the mixture of Gaussians. So let's look like how the generative process looks like. So first we simply generate one of variables from 1 to k with a certain probability. Depending on the value of C, I generate from the mixture of normal distribution. So when C is fixed, so I have normal distribution, but of course when C is generated from category as multinomial, so here I will have the mixture of normal distribution. And after that, having that, I simply try to model expected value and logarithm of the variance of my x, okay, by a certain function, which usually is realized by neural network. Okay, so, and after that I model x. That's how generative process looks like. And of course here you have the assumption about this variational posterior, and this leads to elbow bound. And for example, if I would like to see how this works for overused data set MNIST, okay, so here colors, true colors corresponds to digits, and clusters correspond to this QC over given X function. So I simply choose a cluster which gives you the highest probability. As you see that when simply I train, so I obtain quite nice division into clusters. So this was not mentioned in the last talk, but I believe also it's a powerful method of VAE, of modifications of VAE. So how does it look like for positive unlabeled data? Okay, so let's start with saying that here we have, in fact, approach based on minimization of risk functions. So let's concentrate for a moment on this. So here what happens is that you have just a general approach that you simply write down risk function. And what is interesting here? Okay, so let's look at this. Let's look at this guy. So what happens here is that I have PL standing for positive labeled data. And of course, when I have the positive labeled data, G is my classification function, and I should check whether the sign of G is equal to the sign of Y. Okay? So this is correct form because Y is equal to 1, so this is a true value of my risk in this situation. But imagine now that for the class, for unlabeled class, I simply assign just -1 to everyone. Okay, so of course I commit an error. And I should account for this error, and I account for this error by simply having the second term, which simply, in the case when I have positive but unlabeled data, I give the good, correct version of my loss, and I subtract this guy with simply. That's how it works. Okay? But the problem, what happens here, the problem is that simply I have this PU, positive unlabeled probability distribution, and this is just a big downside here. So, but please know that here no propensity score is modeled. Quite nice expression. But what is price we are paying? We should assume that prior probability is known. And okay, and the second problem is that here you have like the empirical counterpart of this. So empirical counterpart of this will have this population consisting of unlabeled. The wall here, because simply I do not know how to do that. And now the idea is simply to, by using variational encoders, is simply to construct the pseudo sample from this distribution by minimization of it. So this was the idea of those Korean guys who have proposed this VAE-PU method. Okay, so just to cut the long story short, because I'm running away of time, as I see as always. So here, in fact, I am encoding two informations. I have two latent vectors. The one vector corresponds to observation status, which will be HO, and HY corresponds to the status class information. Those will be latent variables, and HY, as before, will be modeled by the mixture of Gaussians, and this guy will be modeled by. And that's more or less how it works. And let's look at dependent structure. So here what is important is that X depends on HY and HY. Simply, we need to have dependence of my X on both observation status and Y. That's for the biased PU, that's the most important thing. Okay, so what happens here? Okay, so I have still 5 minutes. So let's look at TS&E representation. So what happens here? Blue ones correspond to. Okay, let me see. Blue ones correspond to negative. Sorry, once again. So blue ones correspond to negative data. So Y is equal to 1, and here labeled data are green ones, and positive unlabeled are orange ones. Imagine that you are colorblind. Okay, now you would like to associate those orange ones with green ones. That's the idea, but we are blind. Okay? So now the construction of pseudo-sample is simply quite ingenious idea of this paper is simply to take HY for every labeled observation and look for the nearest observation in an unlabeled sample having the nearest HY. Okay? And I simply concatenate HY from the labeled observation with HO from the unlabeled. I put this into my decoder and I simply reconstruct. So in this way, I simply construct pseudo-sample of X's. Okay, so let's look how it looks like. So here you have true labeled guy, and we have this closest unlabeled guy, and this is my reconstruction, and it's quite nice. So the success story. So here it is sort so let's call it average success story because I sort of generate something, but here you have complete. Here the closest guy to this 3 is 5, and I have generated. That's not that good, and that was in fact a point from which we jumping point we just sort of started our research that simply would like to replace this reconstruction by something else, and we have noticed that in fact those guys which are reconstructed are pseudo samples. They do not form the subset of unlabeled data. We like to simply to have reconstruction, but based on having the subset of unlabeled data, and in fact we did simply using one class classification. So this one classification about is simply that simply are trying to distinguish outliers from the idea. And there are some out-of-the-shelf methods. The shelf methods, okay, of course we have considered many others, but simply those four were applied. And what happened is, perhaps this is sort of important here, that we are treating our reconstructed sample from this variational autoencoding as true normal data, as inliers. Okay, and now we would like to find outliers which will be contained in this unlabeled set and will correspond to negative unlabeled data. Okay, those guys will be outliers. Okay, that's our task. And of course, there's a problem here based on that here those are not genuine normal data because simply they were reconstructed. So let's look how the algorithm looks like. You can look at GitHub. There's also software there. So here what we have is that we train our classifying function and we reconstruct our positive unlabeled data. And now what happens is that we, using one class classification, we extract inliers, but in the unlabeled set. And we perform once again minimization of this guy, but using those inliers which simply are contained in this unlabeled set. Okay, and perform this cycle in F1 mode. And okay, so I'm just coming out of time, so very shortly. Okay, so we have several data sets in list, of course, but also CFAR. And we tried to make it binary, so CFAR was called as one class, and machine animal was the second class, STL, also machine versus animal, and one tabular data set was class classification. Okay? And the competitors are baseline VAE-PU, so just what was proposed by now and others in 2020. So it's expectation maximization algorithm and what is called label size method. Okay, so I will skip how the data was artificially labeled using, of course, features. And let's look. Devote one more minute to this slide because I believe it's also important. Okay, so we have our competitors. Red guy is expectation maximization algorithm, and this guy is LBE, and we have VAE-PU, just original one that we have modified a little bit. So here it works a little bit different and better, but here we have four guys who simply are modified by using this OCC approach. Okay, and you see that consistent with the vector. In those guys, this is accuracy. The same picture more or less is about 1/4. And what is quite interesting is that here has a later frequency. The probability of being labeled is a whole set. Okay, so we're just running from 0.02 to 0.7. You see that those two competitors were sort of disastrously for small c. Message, and those guys were quite nicely. So let's once again look at those guys. So it was A cubed, so it's a very recent method. ECOD is also a recent method. Those classical methods. OCC. So more or less the picture is when you look at other results, they look more or less the same. One difference, big difference is for the tabular data for these gas concentrations, when simply in this case we have that LBE method works quite well, at least for us. Okay, so here we have a big difference, and here it is compatible with, in fact, a cube method. Okay, so this is not compatible with better than a C method, but it is, in fact, worse for small. So the message is, in fact, is that OCC helps in this case, and once again, I would like to stress the importance of modeling later positive unlabeled data, but so without star assumptions. So we have some, I believe, exhaustive list of all papers which are concerning biased candidates. Okay, so I'm done.